In this lesson, we will continue our discussion of addition reactions to alkenes. We've already learned how to add two atoms, X and Y, across the two carbons of an alkene via carbocation intermediates. Now we will move to thinking about reactions that avoid carbocation intermediates, and by and large, these reactions go by cyclic transition states. In this video, we will primarily focus on two reactions, cyclopropanation, so making the cyclopropane ring, this three-membered ring of carbon, and halogenation. Just a little bit, we'll look at some variations, but these two reactions will be the focus of our discussion. We'll also just look at alkenes today. We'll look at other nonpolar pi bonds, aka alkynes, in part 2. So again, we're going to think about how these reactions, cyclopropanation and halogenation, differ from reactions that go by carbocations. I did want to make a point of clarification, which is that there's a difference between electrophile addition, which is an elementary step, where there's an alkene reacting with some electron poor species. Here just E+, donating those pi cc electrons to whatever the LUMO is of E, the electrophile. Versus electrophilic additions, they're just a big group of reactions to alkenes. So where you've added two atoms, could be the same atom too, we'll see in a minute, but you've added to both carbons of the alkene. And of course, we learned that for one group of these reactions, the first elementary step was electrophile addition, like we learned here, right? But this is similar to when we discussed substitution reactions. So there was the SN2, an elementary step. And then there was also just substitution reactions, where you've taken some alkyl halide and now there's some other functional groups there. And then this could go by the SN2 or it could go by the SN1. You'd have to kind of think more deeply about it. So we have a similar situation here. So there's an elementary step called electrophile addition, described here. And then there's just a set of reactions where the carbons of the alkene react to make sigma bonds. So you have sigma bonds now to both of those carbons. So speaking of this big group of reactions called electrophilic addition reactions, we have previously learned about electrophilic addition reactions that proceed via carbocations. Let's recall the general mechanism for these reactions. And if you'd like to stop and try yourself first, I would highly support that decision. So the first step of these electrophilic addition reactions that we've learned so far is the electrophile addition elementary step, where we have pi cc attacking sigma star hx. This generates a new CX bond. The CX bond is made CH bond. The CH bond is made to the less substituted of the two carbons of the alkene, because that generates the more substituted tertiary carbocation. So one of the bigger points that I want to make here is that carbocation stability is a very important factor in the outcome of these reactions. So we have the most stable cation formed. And it's an important factor in the regioselectivity of these reactions, so which atom of the alkene bonds to hydrogen and which one bonds to X. It's also important in the stereochemistry. This particular product is achiral and doesn't have any interesting stereochemistry, but we learned that you'll get a mixture of diastereomers often when possible, because this carbocation is flat and there can be attack in the next step, the coordination step, from the top face or the bottom face of that p orbital there, that flat carbocation carbon. So let's show that next step. So then the next step is coordination to the top or the bottom face of that empty p orbital. And that generates the product. But again, we want to keep in mind there are carbocations, and they determine really everything here. They affect which carbons react, the regiochemistry. They affect the stereochemistry, though not really in this example. And they affect whether or not there's rearrangement. There can be skeletal rearrangements. We will contrast these reactions to the group that we're going to start discussing today, and those reactions avoid carbocations. It's this first electrophile addition step that generates the carbocation, right? Because only one atom made, well, let's show you down here, only one atom made a bond in the first step for the reactions that proceed via carbocations. But today what we'll see is some electrophiles, they have good acceptor orbitals and they have a good donor orbital. So there's some donor orbital, I'll just put a lone pair right now, but there's a donor orbital that will attack back. So the HOMO, the donor orbital of the electrophile, can make a bond to the other carbon. So where in the first set of reactions that carbon ended up as a carbocation, this time it's going to make a bond to the electrophile because the electrophile has some donor orbital that can add to pi star CC. Wait, you said pi star CC is not a good acceptor. Usually it's not, but in this case, when both bonds are made at the same time, it is. The reactions today and, in part two, they'll all be a little bit different, but what they'll have in common is that they'll go by a cyclic transition stage or intermediate, or maybe even make a cyclic product, but we will see the cyclic transition state. And then also, we'll see electrophiles that have donors and acceptors. And what those donors and acceptors are will vary, but they will have both. And you'll see both bonds. So you'll see two bonds made at the same time to each carbon of the alkene. Let's think what types of molecules might have good donors and good acceptors. We can begin by just listing what the good donors and good acceptors are, recalling our discussion of FMO theory. Let's start with donor orbitals. So the highest energy donor orbital would be a non-bonding pair of electrons on carbon. Right, just lower energy than that would be a lone pair of electrons on X, so a heteroatom. And then we know pi CC can also be a donor, but the alkene will use pi CC. The electrophile, it won't. It will have a different donor. It's going to be either a non-bonding pair of electrons on carbon or a heteroatom. Now, for the acceptor that the electrophile has, well, that could be an empty non-bonding orbital on carbon. We will actually see that today. Or it could be sigma star CX or sigma star XX. And we will, again, see this today. Okay, so let's start to look at some specific examples of these amazing electrophiles that have both donor and acceptor orbitals. We're going to start by thinking about a reagent called diazomethane. And diazomethane, CH2N2, decomposes to form an interesting species, which is called carbene. So we're going to go ahead and draw the Lewis structure for carbene. Of course, to do that, we need to start by drawing out the Lewis structure of diazomethane. Diazomethane is a pretty interesting looking species. So here is one resonance structure for diazomethane. This is certainly the major resonance structure. But there is a minor resonance structure we can draw as well. We can see we have a lone pair adjacent to a pi bond. So we could draw a resonance structure that looks like this. And in this resonance structure, we'll maintain the positive charge, on the central nitrogen and generate a negative charge on carbon. So this is certainly a minor resonance structure, a minor description of the molecule because you have the negative charge on carbon versus on nitrogen, and nitrogen is more electronegative. However, from the minor resonance structure, we can see how the carbene will be formed. So from the minor resonance structure, think about taking the electrons and that carbon-nitrogen bond and donating them to nitrogen. So what is the name of that elementary step? Yeah, that's a heterolysis. And I understand that it is a weird looking heterolysis. So why might this happen? Yeah, I mean, it might happen because nitrogen gas is generated, which is a super stable molecule and will bubble away. So let's think more about what in the world is going on with that carbon. There's no formal charge on it. You should pause now and see if you can answer these questions. Let's start with the hybridization of carbon. How many electron domains do we see? Yeah, we see 3 domains, which means that this is an sp2 hybridized carbon. If it's sp2 hybridized, it has 3 sp2 orbitals and 1 p orbital that was not involved in the hybridization. These 3 hybrid orbitals, they hold the 3 domains, and in this case, the p orbital will be empty. So hopefully, warning bells are going off. This is the acceptor orbital, this empty p orbital on the carbene. What do you think its donor orbital is? Yeah, that juicy lone pair. So it has a donor orbital and an acceptor orbital. But I'm getting a little bit too excited about that. All right, let's draw out a nice 3D picture here with the orbitals. So we have the lone pair and an sp2 orbital. We have one of those CH bonds going back, the other coming out at us. I kind of rotated the molecule. So the carbene is both electron rich and electron poor all at the same time. So let's take a look at how this molecule reacts with alkenes. When an alkene is treated with diazomethane in the presence of light in this case, and light is serving to promote the formation of the carbene. So we mentioned that a heterolysis step takes place to generate the carbene, and the light helps facilitate that heterolysis step. Once the carbene is generated, it can react with the alkene, and we see that an interesting product is observed, and that product is a cyclopropane ring. All right, so the 2 carbons of the alkene are now bonding to the CH2. All right, this is a CH2 here. This piece is just the carbene, and it's added to both carbons of the alkene. All right, let's take a look. So we have the alkene reacting as a nucleophile, as an electron-rich species, as it does. So this is just our normal pi cc attacking the LUMO of the electrophile, which is that empty p orbital on the carbon of the alkene. So this p is the carbene. And then you have the carbene attacking back. So you have the lone pair of the carbene attacking pi star cc of the alkene. And so because both of these interactions happen at the same time, both of these bonds are formed at the same time. So you do see those 2 bonds formed, 1 to each of the carbons of the alkene. Draw the nice pretty product again. Okay, that's it. Easy peasy. Now, chemists actually like to avoid using diazomethane because it is explosive if not handled correctly. An alternative to cyclopropanation with diazomethane, so we just looked at the same alkene, but we used diazomethane and light to facilitate formation of the carbene. We saw the cyclopropane. That same product can be made with a set of reagents called the Simmons-Smith reagent. And these reagents make what's called a carbenoid species. It's like a carbene. And that species is written out right here. And it's generated in situ, so it means during the reaction by these two reagents. Let's take a look at that reagent. So it has a good donor and a good acceptor. We haven't looked at carbon-zinc bonds before, but you can think about the carbon-zinc bond, this organometallic bond, just like you would think about a Grignard. Organozinc reagents are a little bit more mild than Grignards and organolithium reagents, meaning that there's a little more covalent character in this bond. But still, the carbon is electron rich. The carbon is electron rich. So the electrons in the carbon metal bond, those are the donor electrons. And sigma star Ci, just like we saw in SN2 reaction, sigma star Ci, it's empty, it can accept electrons. So what can occur here? We'll redraw the Simmons-Smith reagent. And the R group on zinc, it's ethyl. It came from up here. I'm just being general with the R. I'm sorry if that was confusing. So pi Cc attacks sigma star Ci. That breaks the sigma bond. And then the electrons in the carbon zinc bond, which you can think about as a lone pair on carbon if you want, or you can think about those as the sigma C zinc, carbon zinc electrons. They attack pi star Cc. So these orbitals are for the alkene. These orbitals are for the Simmons-Smith reagent. And if you want to think about the carbon zinc electrons as a lone pair on carbon, just like we did for the Grignard, that'll be okay too. So you can think about it like this. That's fine. Okay, but the Simmons-Smith has a good donor, has a good acceptor, and behaves like a carbene. That's bottom line. We've examined the Simmons-Smith reaction for generating a carbene-like species. We have examined diazomethane for generating a carbene. Now we'll take a look at a third way of generating a carbene, and that is from chloroform. So upon treating chloroform with a strong base, such as sodium hydroxide, a carbene, specifically dichlorocarbene, is observed. So here's dichlorocarbene. How do you think it's generated? Yep, we're going to deprotonate chloroform. So there's a proton transfer step. To generate the conjugate base of chloroform. And in case you were wondering, chloroform has a pKa of about 15. So the equilibrium constant here is about 10. Okay, and then we have water. All right, well, we're not at the carbene yet, right? So what do you think happens now? Correct. We need to generate chloride and break one of those carbon-chlorine bonds. Let's draw out the conjugate base of chloroform. So now all that happens is heterolysis. I know, so simple when I just say it. Would I expect you to know that heterolysis happens here? No, that's why you're given the product. Oops, sorry, not relieves the formal charge, generates chloride. Okay, so we have dichlorocarbene, chloride, and then water. That's boring. There it is. Cool. All right, let's take a look at dichlorocarbene here. Your turn to draw out a three-dimensional representation of dichlorocarbene and predict how it will react with alkenes. I agree, it's going to look really similar to just normal old, regular old, boring old carbene, where there is a non-bonding pair of electrons on carbon that serve as the donor orbital. And then there is this empty p orbital on carbon, which serves as the acceptor orbital. So how do you think that this species will react with an alkene? What do you think? Well, hopefully you said it will form a dichlorocyclopropane, which is like, this is the most useless thing ever, but it probably does kill some bugs. So let's go ahead and take a look here at this reaction. It'd be cool if you paused and tried yourself. But when you're ready, we will generate dichlorocarbene this way. So first in a proton transfer reaction, just like we showed on the previous slide, that generates the conjugate base of chloroform. From here, one of these carbon-chlorine bonds can break in a heterolysis step to form dichlorocarbene and chloride. The dichlorocarbene is both electron-rich and electron-poor all at the same time. It's an example of one of these amazing electrophiles that we're discussing today. The alkene is electron-rich, and we do have pi cc attack that empty p orbital on carbon. The lone pair, though, of the carbene, it attacks back. So then we have lone pair on carbon, so non-bonding carbon, attacking pi star cc of the alkene. That was a mess, so I'm going to just redraw the arrows down here. We can see both the carbon-carbon bonds are formed at the same exact time. So we have this bond. Let's change colors. This bond and this bond. Okay, so just as we saw, we've been seeing the two carbons, the alkene, make sigma bonds, the pi bond's broken. It just, for the cyclopropanations, they're making the bonds to the same atom, which is why there's a three-membered ring here. Cool. Variations on a theme. Oh, you thought it was over, but it's not, because we can make dibromocarbene. Please pause and answer this question yourself. Really, you've seen it several times now, and you can do it. We notice that similar to the last reaction, there's bromoform rather than chloroform. And then instead of hydroxide, there is potassium T-butoxide. We know potassium T-butoxide is a bulky base, and we'll talk about why it's used in just a moment. But we do know right now that it will deprotonate bromoform to generate the conjugate base of bromoform. So proton transfer. After this anion is generated, the bromide leaving group leaves in a heterolysis step. And we can understand this in two ways. It relieves the negative formal charge that was on carbon, and it also generates a good leaving group. It's certainly favored by entropy because one become two. Cool. And then the dibromocarbene will behave the same way that all the other carbenes behaved. It does have an empty p orbital to accept electrons. And it will react with the alkene. So pi cc attacks the empty p orbital on the dibromocarbene. And then at the same time, that non-bonding pair of electrons on carbon attack pi star cc. That makes both bonds between the carbons of the alkene and the carbon of bromoform, or the dibromocarbene, at the same time. So this reaction is really similar to all the other ones we've looked at, in particular to the dichlorocyclopropanation. The one difference that might pop out at you is the use of potassium T-butoxide instead of sodium hydroxide, which we use to generate dichlorocarbene. So what's the deal with that? Why do you think that potassium tributoxide was used instead of sodium hydroxide in this reaction? Well, let's think about the differences between the dibromocarbene and the dichlorocarbene. Dibromocarbene is more reactive than the dichlorocarbene. Thus, if hydroxide was around, what do you think hydroxide would do? Hydroxide would coordinate with the dibromocarbene. So hydroxide would coordinate with dibromocarbene. However, T-butoxide, this is too bulky to coordinate. Just when I say coordinate, I mean fill up that empty orbital on the dibromocarbene. There's an empty orbital here, right? And we don't want the base coordinating to the carbene. What do we want the carbene to do? We want it to react with the alkene, right? So we don't use hydroxide because it would coordinate to the dibromocarbene. It's perfectly fine to use with dichlorocarbene, which is less reactive than the dibromocarbene. Okay, let's keep going. Let's practice and then let's move on. So provide the missing reagents, reactants, or products for each of the following transformations. Please pause and do this yourself. So we'll notice here that we've added CH2 across the two carbons of an alkene. There are two ways that we can perform this transformation. We can generate carbene. That's where the CH2 comes from carbene. We can generate carbene by reacting with diazomethane in the presence of light, or we could use the Simmons-Smith reagent. So that is generated in situ. So you add diethyl zinc and diiodomethane, and that will also generate the cyclopropane ring product. In the next reaction, there's cis-2-butene, so there's some stereochemistry of our starting material, reacting under the conditions that form dichlorocarbene. So we know from the outset that this will form the cyclopropane ring, but because it's with dichlorocarbene, it'll form the dichlorocyclopropane. Now, these reactions are stereoselective and stereospecific, and that is because the two bonds are formed at the very same time to the same face of the alkene. So all that means is that that cis relationship between the two methyl groups of the double bond, that cis relationship will be maintained in the product. So if it's cis, if the two methyl groups are cis to one another in the starting material, they'll be cis in the product as well. And so the way that you show that, there's two options. You can either just draw both bonds to the carbon that came from the carbene coming out of the page or being in the same direction, or you could have drawn the cyclopropane in the plane of the page and had the two methyl groups coming out. Either way, you're showing that that cis relationship is maintained. Oh, all right. I mentioned that stereospecific word on the previous page. Stereospecific means that different isomers of reactant will give different isomers of product. So you can see there's cis-2-butene, and we're about to look at trans-2-butene under the same exact reaction conditions. And what we're going to see is that different stereoisomers of product are observed from different stereoisomers of the reactant, and that is what is referred to as a stereospecific reaction. So we have the trans-2-butene this time, and that trans relationship of the methyl groups will be maintained in the product because both of the new bonds this bond and this bond, they're formed at the same time, right? We had those two homolumo interactions, and the bonds are formed at the same time. So the cis relationship is maintained. Before we move on to the final problem, oops, I caught a typo. I had been omitting the chlorines from the dichlorocarbene. I'm sorry, and I fixed it for the previous problem as well. I don't want to go back and re-explain that. Please don't make me. So I'm sorry about omitting those chlorines. For our last example, we see we're going to generate dibromocarbene and make that dibromocyclopropane. And there's going to be some stereochemistry here. You can see that the alkyl groups are cis to one another. And so that means that this came from a cis alkene. So we need that cis alkene because these are stereospecific reactions. If it had been trans, trans is a little bit harder to draw with the dashes and wedges to the cyclopropane itself. But if it had been drawn like that, then you might have seen one of these groups pointed down and then the other pointed up. That is trans. Okay, but this was cis, and so we needed to have a cis relationship of the two alkyl groups and the alkene starting material as well. Okay, so you should summarize all these cyclopropanation reactions that we've just learned. I'll leave that up to you. We'll move on now to our next electrophile that has a good acceptor and a good donor. And those electrophiles will be the elemental halogens. We will take a look first at bromine to try to understand how it has a good donor and a good acceptor. So what do you think? What is the FMO analysis for bromine? Well, its donor orbital, its highest energy pair of electrons, is certainly the non-bonding electrons. So just a lone pair. And its acceptor orbital, its LUMO, is sigma star Br Br. Let's just go back to our thought exercise way back at the beginning of the lecture. And we said that non-bonding pair of electrons on either carbon, like in the carbene, or on a heteroatom, like we're about to see, will be good donors. And the acceptor for the carbene, it was the empty p orbital on carbon, but for elemental bromine, it will be sigma star XX. We saw sigma star CX was a good acceptor in the SN2 reaction. Sigma star XX will be a good acceptor for us today. Awesome, let's get to it. So given that information, let's predict the product of this reaction and then propose a curved arrow mechanism. Whatever you came up with is great. What we can say for sure is that the two carbons of the alkene, they're going to make two new bonds. And to what atoms those bonds are made, maybe we have a hard time figuring out right now. So let's just get started and we'll figure it out. So we can pretty confidently propose that pi CC attacks sigma star Br Br. We're pretty comfortable with the alkene being a nucleophile. And bromine certainly is an electrophile. Fill sigma star, break sigma. Now, the whole theme of today is that the electrophile also has a donor orbital. And for molecular bromine, it's a non-bonding pair of electrons on bromine. So those electrons then attack pi star CC, the acceptor orbital of the alkene. That generates two new bonds at exactly the same time. It generates what's called a bromonium ion. This bromonium ion should look to you like a protonated epoxide. What? Yep, yes it should. You have a three-membered ring with a positive formal charge on some heteroatom. Now, this bromonium ion intermediate, it is, as you might expect, electron poor. And it will react through its LUMO, which is sigma star CBr. Now, it will react a lot like a protonated epoxide in that the more substituted carbon is going to be attacked. At this point, we really can't even tell which carbon is attacked based on the product, but I'm just letting you know. It's the more substituted carbon. So now there's a bimolecular nucleophilic substitution step here in SN2. Of course, this a weird SN2 we talked about when we talked about epoxides, where we have the non-bonding pair of electrons on bromine attacking sigma star CBr. And it's a weird SN2 because the more substituted carbon is attacked. Why do you think the more substituted carbon is attacked? Yeah, because like the protonated epoxide, carbon is sharing some of the positive charge with bromine, and the more substituted carbon does that sharing. So we have really a partial positive on bromine and a partial positive on carbon. And then bromide, I mean, it's anionic, but this is not basic. It's a nice stable molecule. So it floats by, it's attracted to the partial positive on carbon, and it reacts with the more substituted carbon. So that's why I say it's a weird SN2, because the more substituted carbon is attacked. Wow, I am talking a lot. Okay, so here we go. Here's the product. Yeah, pretty similar to what we expected. So the two carbons of the alkene have made new bonds to bromine. Oh, we're going to summarize already, but don't you worry, we are not done. An alkene reacts with an elemental halogen, either chlorine, bromine, or iodine, and makes a vicinal 1,2 dihalide. Both carbons of that alkene end up making a bond to X. So we have an X-X addition across the two carbons of the alkene. Now it does go via the halonium intermediate that we looked at in the previous example. And attack on that halonium intermediate occurs in an SN2 fashion. I showed you it was weird. It occurred to the more substituted carbon, but we've got it. We can handle it. So because of the attack on the halonium intermediate, the trans vicinal 1,2 dihalide is observed. So this is there will be an anti-relationship between the two X groups. Okay, so that's really important to keep in mind. Okay, let's keep going. And I want to pause at this point to think about stereochemistry. So what do we know about the stereochemistry of electrophilic additions to alkenes that proceed via carbocations? And then what can we predict or say so far about the stereochemistry of electrophilic additions that proceed via cyclic transition states? It's actually a little more clear if we use this alkene. We can see what a mess the stereochemistry of electrophilic addition reactions that go by carbocations is. So we have proton transfer or electrophilic addition in the first step. And this can happen to either the top face or to the bottom face. So to the bottom face or to the top face of the carbocation or of the alkene. And carbons 1 and 2 are exactly the same, so I just protonated carbon 1. That generates this tertiary carbocation, and now the carbocation is going to react. The carbocation is reacting through its p orbital, and so you can have addition to the top face of the p orbital or to the bottom face. So when the halide attacks, it coordinates. That can happen to either face of the p orbital. So there's 4 possibilities then of what you'd end up with. So those 4 stereoisomers represent a racemic mixture of diastereomers. of the product. So I would not at all call this, it's not stereoselective, it is not stereospecific, it's a mess. So the carbocation, the electrophilic addition reactions that precede by carbocations. But we've seen sort of the opposite with the group of reactions we're discussing today, where the electrophile makes both bonds at the same time. Because both bonds are made at the same time, we've observed stereoselective and stereospecific, where two isomers of the reactant give two different isomers of product reactions. We observe the stereoselectivity and stereospecificity of cyclopropanation reactions in these examples. So this example and then the next one, which we'll scroll down to in just a moment. So when cis-butene is treated under conditions that form dichlorocarbene, we observe only this cis isomer of the product. So that means it's stereoselective. The methyl groups are only cis to one another. They're not trans. This reaction is also stereospecific because the cis-2-butene makes a cis product and the trans-2-butene makes the trans product. Wow, you guys, this is embarrassing. Trans. Okay. We'll see something similar with halogenation. So halogenation reactions are stereoselective. They only form one stereoisomer of product when multiple stereoisomers are possible. And stereospecific. Different stereoisomers of starting material lead to different stereoisomers of product. I would like for you to try to explain this observation. So we can see that the trans hex-3-ene and cis hex-3-ene lead to two different products, the RS from the trans and the SS from the cis. So how did you understand that? I think it's easiest to understand this through a mechanism and easiest to understand this with the trans hex-3-ene because it behaves similarly to what we might expect. I mean, well, they both do, but I think it's easier to see this with the trans. So we have our pi CC to sigma star ClCl. That's just our typical electrophile addition. What is atypical, at least before today, is that then the non-bonding pair of electrons on chlorine attacks pi star CC. So both species, the alkene and the elemental halogen, donate and accept electrons. That will generate a chloronium ion. And that chloronium ion, because the two bonds are formed at the same time between the carbons of the alkene and chlorine, that chloronium ion will preserve the stereochemistry of the starting material, which was trans. So I have those two alkyl groups trans to one another. Chloronium ions are electron poor. They accept electrons. So from here, we will have electron-rich chloride, which was generated in the first step when the sigma bond broke, attack. And we will attack. Carbons 3 and carbons 4 are exactly the same, but this is an SN2 reaction, so it occurs with inversion of stereochemistry. So this stereoisomer of product is observed. The chlorines are anti to one another because of the attack, the SN2 attack on the chloronium ion with inversion of stereochemistry. So that makes the anti-chlorine. And then the alkyl groups are anti to one another. That has to do with their relationship in the starting alkene, right? They were anti in the starting alkene that was preserved in the chloronium ion, and it's preserved in the product. Just to be clear by what I mean by anti, since it's been a while since we've talked about it, I have taken this product, the RS product, and I've drawn it in a Newman projection by looking down this bond. We can see that the chlorine groups are anti. That is because of the SN2 with inversion on the chloronium ion. And then we can see an anti means a 180-degree dihedral angle, right? And we can see that the alkyl groups are anti to one another, another 180-degree dihedral angle. And again, that is coming from their trans relationship in the starting alkene. It was a lot easier when we had the alkyl groups locked in a ring, right? When the alkyl groups were locked in a ring, it's like, of course, it's mixed trans. But look, I mean, the cis relationship between the alkyl groups, like they're still cis, that's maintained. Okay, so you have the anti-relationship of X due to the attack on the halonium ion, and then you have this cis relationship, at least this time, for the alkyl groups because they're locked in this cis conformation. So nothing ever changes. It's easier to see what's going on. It'll be harder for this next example. Okay, we have another cis alkene here, but this time it's not locked in a ring. It's acyclic, and we can think about why the SS product is observed. So we will have the same first step. So attack on sigma star ClCl and then attack back to generate the chloronium ion. But this time in the chloronium ion, the alkyl groups are both pointed out at us, right? That cis relationship from the alkene is preserved. And then from here, we can have chloride attack. Chloride can attack either of those carbons. It attacks sigma star sigma star CCl with inversion of stereochemistry. And it will result in an anti-relationship between the two chlorides. And once you get it all drawn out, it looks like this. Now, this is not how we usually draw molecules, and that's why it doesn't look like the final product that I drew here. And so to kind of explain that to you, I have drawn a Newman projection down this bond to show you that typically we draw alkyl chains and they're zigzag, they're all anti-conformation. And that's not what we have. The alkyl chains here have this gauche relationship. And that's fine for you to draw products like this. If I ask you to draw a product and you draw it like that, that's fine. I can figure it out. But it's not how I draw them because I draw the alkyl chain and it's all anti. It's zigzag conformation, just like it's shown here. And I don't want you to get confused by that. So what we can imagine doing is we can imagine grabbing one of these alkyl groups, grab it on the back, and rotate it until we get the alkyl groups anti to one another. So we will do that. We will do it way up here probably. So let's redraw that. So we had to bring it all the way over there. And then it should look like this. Let's just double check. Yep. Okay, so now you can see you have the anti-relationship between the alkyl groups. And this is just how we typically draw alkyl chains because you guys already know that is the most stable conformation of an acyclic alkane toward all the carbon-carbon bonds have this anti-relationship. Okay, but when you do, now we can imagine looking at the molecule from here, and that helps me to draw this picture. You can see, oh, hey, the chlorines, they are syn to one another. They're on the same side of the page when I have the alkyl chain zigzag. Now, don't be confused because that's not how the chlorines added, right? The chlorines added anti, but then there was this bond rotation, and in the bond rotation, they end up syn. So if you see a product where the halogens are syn, all that means is that this is not the relationship of the alkyl chain in the alkene. And it's not, right? The alkyl groups were not anti in the alkene. They were cis. No big deal. If that didn't make sense, like that end part, it'll make more sense with an example. Okay, so let's just make sure you have the point of this page, which is that different stereoisomers of the product, excuse me, of the reactants lead to different stereoisomers of the product. And that makes this a stereospecific reaction. But in both cases, there's an anti-addition of the chlorides because of this halonium intermediate upon which SN2 occurs. And then there can be some complications if we allow for bond rotation like we saw here. But always for halogenation, the halogens are added in an anti format via the halonium intermediates. We're going to come back to the idea of stereochemistry in a bit. We're going to look at a slightly different variation of this reaction. And that variation involves adding water to the mix. So if you like, pause and predict the products of this reaction. So for all of these electrophilic addition reactions, we're adding 2 atoms across the 2 carbons of the alkene. And that's no different in this case. I'll just let you know in this case, if you'd like to really for real stop and predict, we're adding bromine and hydroxyl across those 2 carbons. That's the net addition. Okay, so if you guess that the first step is attack of pi CC on sigma star BRBR, you would have been correct. That breaks the sigma bromine-bromine bond. What do you think happens next? Yes, at the same time, bromine, with its non-bonding pair of electrons, attacks pi star CC. This generates the bromonium ion. And now, because both bonds to bromine were formed at the same time, the stereochemistry of the starting methyl groups is maintained. So they should be trans or anti to one another. So starts out trans, still trans. Now that we know the bromonium ion is electron poor, in the first step here, this generated bromide, which is an electron-rich species. And in previous examples, we had bromide open up the bromonium ion. But in this case, we also have water around, and you need to consider what is a better nucleophile, water or bromide. But also you could think about what do you just have more of? And there's way more of water. It's a solvent or a component of the solvent. So there's tons of water. So water opens up the bromonium ion, and it opens it up in an SN2, just like we've observed before. So there's an SN2 where the non-bonding electrons on oxygen attack sigma star CBr. So we'll have this anti-addition of water. That generates a protonated alcohol, which has a pKa of about -2. So this will be deprotonated by water to generate this product. So I'm going to write it 2 different ways. So to generate this product, but as I was mentioning before, typically the alkyl chain is drawn in the plane of the page. It is here already in the anti-conformation, so I don't really have to do anything fancy. And then this is the product. And if you were not convinced by that, you just would assign Stereochem, or you'd assign R and S. I assigned R and S, and I'll point out a few things. You can see in the SN2, when water attacks, there is an inversion of stereochemistry. And then when I rotated the molecule in space a little bit just to get the alkyl chain, in the plane of the page, the way that it's traditionally written. And I can show that by R staying R and S staying S, that all I did was rotate the molecule in space. I didn't change any absolute configurations, which would not be good because we're not breaking or making any bonds. I'm just rotating the molecule around. Okay. Your turn. So there are two possible diastereomeric products of this reaction. I'd like you to draw both products, predict which one is formed, and then use a curved arrow mechanism to explain your answer. Ready, set, go. When an alkene is treated with elemental halogen in the presence of water, a halohydrin is formed. So bromine and hydroxyl add to those two carbons of the alkene. Now there are two possibilities. Those two groups can add anti to one another, or they could add syn. Anti and trans are similar, syn and cis are similar. Well, we learned in the previous example that this reaction proceeds via a bromonium ion. And so the two groups are going to add anti to one another. So the bromine and the hydroxyl add anti to one another. So the stereoisomer of product, the diastereomer that's formed, is this anti-diastereomer. The anti-diastereomer is formed as a racemic mixture. Addition of bromine occurs to either the top face or the bottom face of the alkene. Of course, these two bromonium ions are exactly the same. So the racemic mixture comes from the attack of water. Water can attack either of these two carbons, or it could attack the other carbon of the bromonium ion. It can attack either one, it just has to do so from underneath, right? And because of that, both enantiomers of the product are formed. And you can write it all out and convince yourself of it if you would like. Okay, let's stick with halohydrin formation. So now you know that anti-addition will occur. We've talked about that ad nauseum. Let's draw the structures of the two possible constitutional isomers of the product of this reaction. So you know it's going to form a halohydrin. You know that Br and hydroxyl, bromine and hydroxyl, will add across the two carbons of the alkene. But now this is an asymmetric alkene, so we need to figure out which of those carbons will add to which of these groups. So please give it a try. When in doubt, draw a mechanism. So what we can say for sure is that pi CC attacks sigma star, BR, breaking the bromine-bromine bond, and then the non-bonding pair of electrons on bromine will attack back. Carbons 1 and carbons 2 both form a bond to bromine at the same time, generating the bromonium ion. The bromonium ion can form on the top face, which is what I'm going to show here today, or it can form on the bottom face. Either way, so I'm going to put a plus minus because that bromonium ion is chiral and both enantiomers exist. Now, the bromonium ion is electron poor and it will be attacked by water. We've already discussed that. Bromide was formed, but there's much more water around. So water will act as the nucleophile here. And now water can attack either carbon, just like we said, water can attack either carbon. Same. Water could, in theory, attack either carbon. On the previous example, the two carbons had the same substitution pattern and were the same. But in this situation, the two carbons are different. So if we attack carbon what I labeled as carbon 2, that will generate an intermediate that looks like this. So you can see there's that anti-relationship between the water that attacked and between bromine, which is what we expect. All right, so we would have this product. Now the other, and it will be a racemic mixture, right? Okay. Now the other possibility is that water attacks not what I've labeled as carbon 2, but what I have labeled as carbon 1. Talking and writing, just such a challenge. Okay, so that would make this intermediate again as a racemic mixture because it started out as one. Again, with an anti-relationship between the water and the bromine. So the pKa of about -2, so it gets deprotonated by water. And that would form this product as a racemic mixture. Okay, can we all see that they're constitutional isomers? Yes, we can. They are definitely constitutional isomers. They have the same molecular formulas, but they have different connectivity of atoms. Hydroxyl has added to carbon 1 in the first example. Hydroxyl has added to carbon 2 in the second constitutional isomer. So do you think they are both observed, or you think that one is favored over the other? I gave you a hint quite some time ago, and I don't really expect you to necessarily remember that hint because it was a long time ago. The only observed product of this reaction is the one that I have just boxed. And that product results from water attacking the more substituted carbon of the bromonium ion. And now, of course, that is weird because this is an SN2-like reaction. This is an SN2-like step. So it's weird. Now, the clue that I gave you was that you should consider the bromonium ion analogous to a protonated epoxide. And we know that when protonated epoxides are treated with neutral nucleophiles, the more substituted carbon is attacked. And this is because the protonated epoxide can be described in a way like this, where the more substituted carbon has a longer bond to oxygen. And this allows for sharing of the positive charge between carbon and oxygen. And sharing stabilizes electrons, it stabilizes this charge intermediate. And that's the same for the bromonium ion. So for the bromonium ion, the more substituted carbon of the alkene that is now bonded to bromine shares the charge with the heteroatom. And for neutral nucleophiles like water, they're just attracted to charge. And so it floats by, it's attracted to the charge, and the negative electrons, react with the more substituted carbon. So for bromonium ions and protonated epoxides, the more substituted carbon is attacked because that neutral nucleophile is just attracted to the partial positive that the more substituted carbon is sharing with either bromine or oxygen. Let's summarize. This video is long. I feel like I am just speaking in circles, and I'm really sorry about that. But hopefully you got something out of this lecture, and you can always ask me questions. All right, halohydrin formation, halo, halogen, hydrogen, hydroxyl. This occurs when an alkene, and I have two examples so we can just decompress and unpack what we just talked about. So a symmetric alkene versus an asymmetric alkene. It's when an alkene is treated with an elemental halogen in the presence of water. The product is this vicinal halohydrin, where X, the halogen, and water have added in an anti-fashion. Now, for the asymmetric alkene, there's just one tiny wrinkle, which is that the hydroxyl adds to the more substituted carbon. So hydroxyl adds to the more substituted carbon, and this is consistent actually with Markovnikov's rule. I know you don't believe it, right? But it is. It's consistent with Markovnikov's rule. And one of the ways that I phrased Markovnikov's rule to you is that the more electronegative atom of the two adding, so we have X versus oxygen, the more electronegative atom of the two adding adds to the more substituted carbon. And that is what we have happening here. And how can we understand? Is it just is it coincidence that it is consistent with Markovnikov's rule? No, it's not coincidence. There's no cation here. There's no full cation because of the halonium ion, but there is carbocation character. The more substituted carbon shares the charge with the halogen, and that carbocation character results in Markovnikov selectivity. Okay, so we get the anti-isomer, hydroxyl adds to the more substituted carbon. So that's stereochemistry check, regiochemistry check. And then there was just that that added thing, which is for acyclic alkenes. So here's for the trans. Let's say we added X2 in the presence of water. It would be really straightforward. You get this question right 100 out of 100 times, right? You have their anti-addition. But with a cis acyclic alkene, we're still going to observe anti-addition. The only added wrinkle here is that oftentimes the carbon chain will be rotated into its zigzag conformation, just like this. And when you rotate around that bond, that's going to put the hydroxyl on the same side as the X group. But don't worry, when they added anti. The rotation just puts them on the same side, makes them look cis. Okay. I know, we're so done. All of us are done. I just have to show you one more. And this is a variation on a theme. So let's say we take the alkene and we treat it with bromine, but this time instead of water, there's methanol around. Methanol can behave just like water, and it will generate what's called a vicinal halo ether. So there's a 1-2 relationship between the functional groups. That's where the vicinal comes from. Ether this time, because instead of OH, it's OR. It's the same exact, it goes by the same exact mechanism. You have bromine add to make the bromonium ion. Bromine has to add to the same face of the alkene. And then methanol opens it up in an SN2 elementary step. It could attack either carbon of the bromonium ion, so that leads to a racemic mixture of this intermediate, and then this intermediate is deprotonated with methanol to generate the product. So this is the same exact mechanism as we saw for halohydrogen formation. Same exact mechanism as for halohydrogen formation. And all the same considerations. So see if you can summarize haloether formation, just like I summarized halohydrogen formation here. I know, sigh of relief. I forgot the summary slide, so make sure that you summarize, and then you should revisit the learning goals for today. I am not going to, I've been summarizing as we've gone, so I'm not going to do a big summary here, but just remember what we discussed at the very, very beginning. So we have thought about these types of addition reactions where the electrophile has a donor and an acceptor orbital. So we've seen cyclic intermediates and cyclic products and cyclic transition states, and it has really profound consequences on the stereochemistry, the regiochemistry of the product, and then, since we don't have carbocations, we didn't see any rearrangements today. So make sure that you make a reaction chart. You learn all the reactions that we talked about today. I tried to give you some help with that by summarizing as we've gone reaction by reaction. It's time to practice. Really, you must practice to get this stuff down. Okay, good luck.